So now let's start with creating a model for a lever mechanism. So in order to start with, we'll first create a blank MATLAB model, and let's first of all save it in a folder where we created our first file. And remember to name them as actual file, which is going to represent something and its name represents what exactly it is, right? So maybe this is your first lever experiment, or let's say your first lever model file. I'm going to name it as lever1. So I've saved it as lever1.slx file, and this can be accessible in the same folder, which is our current directory. Now I want to start with a lever mechanism. So instead of going into the Simulink library file and searching here for a lever, we can directly search the same in our untitled model itself. So I'm going to search here as lever, and here is a foundation library of mechanical and mechanisms. So here we have a lever available, and what you can see with the lever is actually the 3 points A, B and C. Now how do we start modeling with this, right? So, or what exactly we want to do? Let's say we want to apply some force to A point and get the output on the B by keeping the C point as a fixture or as a reference. So in order to do this, first we have set our basic objectives, what we want to do with this. Now it's the time to double click on this lever and open up the help file. So when you double click on the block parameters, this window will open and it will explain you lever mechanism in its generic form, and it's known as a free or summing lever, and it has 3 lever pins, and this is how it is going to affect. Now what you can input, what you can predefine for this lever as a physical model is the length of AC arm and the length of BC arm. So the AC and the BC arm you can fix, and their length can be in the meters. So let's keep it as 0.1 by default. Now if you see here, you can actually open up the source code and see how the lever looks like. So this is how the lever diagram, or let's say a lever as a block, is converted into .ssc file. So let me give you an idea. So this is an MATLAB editor, and here you can see the lever.ssc file, which is nothing but a Simscape code file. So Simscape code is a different language than the MATLAB M script. It's slightly different, but it will give you the idea about what exactly it is. So if you are not able to see it properly in the screen, let me go to the configuration and let me help you to how to configure the font size. So for configuring the font size, which is here, you have to click on the preferences. So when you click on the preferences, it will give you the option to change the font size. So in this case, what you see here is a font available as in the middle line. So when I click on the font, you can change the font, but I'm basically interested in changing the size of the font from 10 to, let's say, 24. So this is going to be the demo, and if you click on OK, now you will be able to see it properly. Now you have changed your system font, and you might have done with the same procedure in your scripting exercises. So what you see is there are 3 nodes created, A, B and C, and all the basic values which are given in the model, they are now available here, and the parameters are specified over here. So here you have the variables which are forces at A, B and C, and this is basically the calculation which is related to all the parameters. So this is how simply your lever is converted into an equivalent Simscape code. This is just for your information, and likewise in the background, all this whatever is affiliated with this block, that will come here, and the MATLAB solvers are going to execute this program. So let's come back to the model environment again, and here we have the lever block, and we want to assign some values. Let's say we keep the values same, And now we have seen the source code. Now let's click on the help over here. So you can see the help menu of each block, which is located in the box in the bottom side of the block parameter. So if we click on the help, the MATLAB documentation related to lever is going to come up, and whatever you see, that theory associated with the lever, that will be reflected over here, right? So whatever are the forces, whatever is the LAC, LBC, which are the lengths, and FA, FB and FC, all these calculations or the fundamental theories are explained over here, right? So if you fix the point A or maybe any other point, whatever are the cases with the forces acting, that is going to change, right? And how you need to assign the port, right? What is the meaning of A, B and C, and you can actually run a linkage mechanism help example as well. So let's now, after reading enough the technical information about how the MATLAB has modeled the lever, let's start modeling itself. So now we have decided to apply some force at point A, and to understand or to know whatever are the forces available at point B, keeping the point C as a reference. So now there are three things. One is I need to find a reference for C, I need to find some output, or we need to observe something at node B, and we need to apply some input at point A, right? So how do we carry out these things, right? So in order to do this, we have to search out for the source of the force, right? So I'm going to search SOURCE source, and which is going to be force, right? So I'm searching out force and source together, and here is what something I have got is ideal force source, and which is, here you have to read it, a foundation mechanism, right? So the foundation library and the mechanical sources, so this is going to be the right choice for our case. Now what is the right choice for your first model, that you have to decide, and you may require to actually figure out a couple of things on do some very fundamental exercise and study in order to choose the correct block for your case, right? So your case may be different than this, and how do you get help, right? So you need to search out for the various things, right? Let's say for point B, we want to find out something is related to force observation, right? So we want to observe the force. So if I write here observe the force, probably there is nothing like this, right? So observing the force is not directly available as a Simulink library block, and so we need to modify our search. It's not an observe, let's put some technical word where it's a sensing, right? So if I type sense or a sensor, right, I'm going to get this block as a result. It's an ideal force sensor. So let's say we have now an ideal force sensor available, right? So, and if you want to remember, right, what this block is about, you can actually turn on displaying the name. So here is the case where you can actually show the block name, right? So if you select the middle parameter, then the block name will be shown. So I'm going to enable it for all these blocks, right, so that I can remember what is the meaning of this block, right? Because this block, if I'm seeing it at the first time, I may not remember what this is, right? Or for this block, I am not sure going to be this is a sensor, right? So if we click somewhere else, its name is gone, right? In order to keep the name, we can keep it as show block name from this menu option. So now we have the ideal force sensor, a lever and a force source, right? Now again, we need to go into detail of what is what, right? So it's always better to read about those blocks before you run your simulation. So how to do that? So basically, if you read out this R and C, what is the meaning of R, C and S? So port S is physical signal port, right, through which the control signal that drives your source is applied. So S stands for source, R is going to be the output of the force where you apply the force, which is to be connected to A in our case, and C is nothing but the casing or a common reference, right? So if we do this, I need to probably rotate this. And how do I rotate this block? Because I need to connect the R with A and it may not look properly, right? Let me learn how to rotate this block in such a way that it is going to be aligned properly. So you can right click and rotate and flip, and you can rotate it clockwise by Control R, which is a short key. So here is a rotate and flip option for you where you can basically rotate any block. So I'm going to press now Control R, and okay, now probably it looks better. So here we have connected the R point to A point, and whatever is going to be the force value which we have to apply over here as input, right? So now we can apply some input which is going to be a number, or you can apply any other signal as well. C is going to be the common reference. Now let's connect a similar way what is going to be a sensor. Now in order to run this model, we need to understand how the sensor works, right? What is the input to the sensor and what is the output? So let's again learn from this help over here. So R and C are other ports, and connection F is a physical signal port that outputs the measurement result, right? So here R and C are going to be the similar case, the F is going to be the output, right? So I'm required to connect R with this part, right? Now C is going to be our common reference over here, and F is going to be the output in case of a number. Now with this basic exercise, let's create a common reference which is to be connected to the C point, right? So how do we find out the reference, or what is going to be the case? So here all these blocks are of same green color, and we can find out a reference which is linear motion reference, right? And if you search from a basic term reference, it is going to be so many different references, right? So probably you need to fine tune your search in order to find a correct block for you, and this is going to be an exercise which may take some time, and you need to invest your time initially to search out what are all the blocks, right? And this is going to be a reference, and let's say this reference is going to be some rotational part, right? So mechanical rotational reference. Now do we have any rotational references or do we have any rotational parts over here? No, I made a mistake, and I need to actually find linear motion references, right? So or instead of a linear, if I type linear, I'm not getting any result. Let me search for translation, right? So here comes the translation reference block. So this is going to be a mechanical translation reference block, and let me figure out, let me show the block name, and if I connect this, I need to connect now all these points, right? So C is one connection. Now how do I connect this C? I can right click over here and connect it, or maybe I can take up this arrow and connect to this part. So now here we have a C block, and now we need to connect this to another similar reference, and this is intuitive, right? Or where it appears automatically that where you want to connect. Now if you are making some wrong connection, let's say for example you are connecting this F block over here, right? Or you are trying to connect this F block over here, which may not be right. So let's see what happens, right? So your connections will appear always in red, right? So when your connections are firm, then only they will appear as perfect as green dot, right? So F is the output of the sensor, which we cannot connect to the reference, or it's not going to be a green signal. It's not, its signal type is going to be different. Remember here one thing, if its signal type is going to be green, then we could have connected it perfectly. So then logically it's not correct, but the MATLAB will not show any error. So this is going to be the error which is generated by the modeler itself, or the person who is going to create the model, right? So if it is of green type same signal, we could have been able to connect to this place, right? But which may not work in our example, or which is going to be logically incorrect. So syntax wise incorrect are two things, or the model will not allow you to make any syntax error, and therefore it's going to be more clean, right? But you may have some different errors which you are not able to have visually available as this one. Now what we want is to give some input, and we want to visualize some output. And how do we do that? I think it's simple, and now you know some blocks which are, let's say we connect a display over here, and which is going to display the output force, and let's create some constant number over here, and which will give some input. Let's say this constant is value 10. So now let me try to connect this constant to S part and display to the F part. So I'm going to connect this to this value, and okay, probably we are making some error. We are not able to connect it, right? See the red part over here, and this is a false connection. This is not connected at all. Now why we are not able to connect? Because this is going to be a Simscape library, and it is going to be a physical system, and this is going to be a number. So we need to convert this number into an equivalent signal. So how do we do it? So we need to convert this Simulink variables, or let's say a Simulink environment signals, into physical system. So what we need is Simulink to physical system converter, and that can be found by Simulink to PS converter, which is the very first choice coming up in the search result. So here we have a Simulink to PS converter, and I'm not going to have this block name displayed because it may occupy some space in my block diagram. So now I'm going to give this as input. Okay, now it's able to connect, and let me connect this to S. Now we are able to make another connection, right? So look at its difference in color. Here is a black which represents the Simulink. Here is some other color, red, or it may be applied to green as well. So do you have any idea what we will require to connect this? Because this will also be not connected directly. So what is the type of block we have chosen here? It is Simulink to physical system converter. Now the display is also of Simulink type. So what we need is another converter which is physical system to Simulink converter. Now in order to get that block, I can write like PS Simulink converter, right? So let's try to connect this and this one with this one. Okay, now it's going to be perfect. Now let's try and run this model for 10 seconds, and we are giving some input as 10, and AC and BC length are equal, right? So this is going to be a case with a seesaw. What we will observe in the output, what will be displayed at the end of 10 seconds here? Any guess? So here we are applying 10 constant value of force to the point A, and according to the AC and BC length, the forces will be calculated over here, and the B part is going to experience that much of deflection, or the B node is going to experience the change in its position, and that will be displayed over here, where C is the point of common reference, right? Now what will happen if I click on run? Are we able to run our model now? Let's try and understand. So if I run the simulation, here comes the diagnostic viewer, and it is suggesting something to us, right? Let's try to understand what is suggested by the diagnostic viewer. So this is the diagnostic viewer window, and if we have any errors, if we have any logical or syntax error, it is going to show up over here. So if you read out this diagnostic, what it is suggesting is this, right? So there is ideal force sensor, ideal source, then there is a lever, and each physical network must be connected to exactly one solver configuration block. There is no solver configuration block connected to physical network with following blocks, right? So this is an error, right? So the Simulink is asking for simulation configuration or solver configuration block. So how do we have the solver configuration block? So this block is missing in our case, and let me find out a solver configuration. So this solver configuration is going to be okay, so here comes the search result as solver configuration, and solver configuration is nothing but fx equals to 0. What is the meaning of fx equals to 0? This is going to form an equation, right? So when we have such a system where we have some Simscape code running in the background for this model, and this, we need to apply some common reference or common solver, right? And we can connect this solver reference to this part, right? And you see that if we connect like this, it's not going to be correct. It's going to be correct, then it will appear as a green dot. And now I can release my mouse click. So now we have a solver configuration block. Let's see what is inside this block. So this is solver configuration. It defines the solver settings, and here we have so many parameters. Now what is the meaning of all these parameters? Okay, let's keep all this as it is, as the default value, and maybe if you are curious about knowing more, you can click on the help and try to understand what's happening and how to put all these values. But at this moment, let's keep it default value, right? Now does it solve our problem? Right now, are we going to have the diagnostic viewer or error coming up again? Let's try and hit the run button. No, probably not this time. Then okay, what is the result? Okay, result is -10. Okay, here we are able to run our simulation of a lever perfectly. Why? Because 10 is the value of the force which you are giving, and 10 is going to be the force applicable at point A, and what you get at point B is going to be -10. So exactly the theory behind this applies, and now we are able to run this all equations, and we are able to get what is the value of the output force at point B. So this is our first simulation. And what will happen if you give some other constant value, right? What will happen if you give let's say maybe 100? Let's say if we give 100, the answer is again -100, because whatever the force you apply, if these two lengths are equal, then whatever is this 100, the negative of that, or whatever is the input, the negative of that will appear in the output. Now let me try with the 100 same value and change this to AC arm length to something other than 0.1. Let's keep it as 0.4. So now I need to press OK over here in order to get this change affected, right? You can use OK or apply. But if you double click on the block and if you click on cancel, the changes are not saved, right? So I'm clicking on OK, and now the changes are applied. And if you can check again by double clicking, and now it's 0.4 and 0.1. Now what do you think is going to be the answer? Now the answer is going to be exactly according to the ratio of this two lever length, and that will be displayed over here. So if we run the simulation, let's say our answer is -400, because the length is now in a ratio which is 4. So if you take this ratio, AC by BC is going to be the 4, and that is affecting the output. So this is how you can create a very fundamental lever simulation. Now there are so many other factors affected to it, where you may try to add some other things, right? Where you may have some other mechanisms affected. You may have some friction block, you may add some spring mass and damper kind of a thing, and try to visualize what is happening. So this is how you can create your first Simscape mechanical system simulation.